Alright, looks like we got all the bits flowing. Welcome back to the stream. Tuco has taken my chair. I mean, I guess it's really his chair, but that's what we're working with today. I don't think he's moving. Aw. Oh, honey. Yep, cat channel. Here's a glimpse of what we've got for later. I actually put a webcam above the LCD so we can see despite the terrible viewing angle. So we've got a bit of a PC hardware mystery here. This machine is mostly 486 PC compatible, it seems. No luck in getting it to boot Linux, though. So far I've tried syslinux and grub, and I didn't choose to dive too far into debugging syslinux. I just looked kind of briefly at how it was maybe failing. It seemed pretty late in the boot up process. Grub is a bit more useful since it has a fairly powerful console, and most of Grub itself seems to be working in this system. But as soon as I try to use Grub to boot into anything, even just rebooting Grub itself by chain loading the MBR, the system just crashes in an unknown manner. So I've got a bunch of debugging tools now. I've still got a logic analyzer attached to the I/O bus so that I can see a lot of the interactions between the CPU and the peripherals in the system. I've got this serial port now attached to a Raspberry Pi where I've been running Gdb, and that's been super useful, especially now that I've got a copy of grub that I've compiled myself, and so I've got all the debug symbols for it. So that's been kind of useful. We tried just stepping through the failing part of the boot up on yesterday's stream, and that led to kind of a strange place for it to fail. So from what I can glean so far about Grub's boot up process, they have fairly high-level code to do most of the work in preparing the memory environment for the new OS, and just they try to have a pretty nice environment for doing the high-level decisions and figuring out what goes where and actually loading things into memory. And then they transfer control to this very low-level piece of code, which actually does the final step of moving chunks of memory into their final locations, and then setting up the CPU state in order to jump into the new operating system. And that piece in Grub is called the relocator, since it's mostly about relocating chunks of memory from place to place. And there are different versions of this relocator for 32-bit and 16-bit entries. I've been mostly focusing on the 16-bit version, but from my limited amount of testing, I've been getting the impression that the 32-bit version probably has a similar problem. And the debugging yesterday was kind of the first chance we got to see where in the relocator it might be failing. And so from stepping through with the Gdb stub, it seemed to be failing in the middle of a large memcopy that was directing some temporary data for the relocator into a buffer in low memory. This is in an area below the first megabyte, something that would have traditionally been like DOS memory. Stuff that shouldn't be memory mapped I/O. It should be way lower than where memory mapped I/O usually goes. But, I mean, the system is full of an unknown amount of non-standardness at this point, because it only needed to run their custom application. We don't know what might be customized and or broken about the BIOS. So there could just be some weird hardware in some place that it usually shouldn't be. There also could be some memory area the BIOS is using, although the BIOS should have very limited opportunities to get control in this case. The interrupt vector table that controls where the CPU actually directs control when hardware events happen, that's under control of grub, and specifically it's actually been wrapped by the Gdb stub. So unless we're actually trampling on the Gdb stub's interrupt vector table, we should still be able to handle debug traps. And we should double check this, but my understanding is that the Gdb stub's interrupt vector table is up in fairly high memory, above a megabyte, in the vicinity of where the modules for Gdb would be loaded. Oh, Tuco left me my seat. You want to sit here, Tuco? Oh yeah, one cool thing about the Gdb stubs in Grub is actually I didn't have to compile Grub myself to get those. Those were in the regular release version. So if you want to debug Grub without symbols, you don't even have to compile it. I just wanted the symbols. And actually, depending on how your distro packages Grub, you might be able to get the symbols from your distro packages. I didn't look super hard for that in Alpine, but I just ended up compiling Grub from Git, and that wasn't too much of a pain. So yeah, I made some changes to the grub config file so that we can boot into Gdb without any annoying human interaction. So now I can power cycle it and get right into serial debugging. Do you want to actually go? So yeah, that's basically the shape of what I've got now. So I've got a couple of memory addresses where I think there might be something weird happening, but I don't really know anything beyond that. I don't know whether it's something on the system that I'm trampling, and that could be a hardware thing or a BIOS thing, or whether it's just something in grub that I'm not aware of that is essential for the serial debugger to work, and we're clobbering that in the relocator. So got some debugging to do. I wanted a bit more leverage for the debugging, so I thought I'd try using the Gdb Python integration instead of just banging away at Gdb, and I wanted to actually be able to script a little bit of this, so having the machine boot directly into the debugger should be pretty useful. If we need to, we can even do things like automate power cycling if we end up needing to do any sort of extremely crashy sort of automated testing. But so far, most of the stuff we have been doing isn't extremely crashy. So my first, I don't know, there's a lot of things we could look at. Like, one of the things that I got just very slightly into on the last stream was like just dumping those memory regions and seeing what's in there and trying to see what, if anything, causes them to change. I think the most straightforward way to see if anything really odd is configured on this system is to try dumping the registers on the system on chip. So that was kind of the first thing I wanted to use a Python script to do. So that would just involve doing some I/O port accesses. And actually, it's actually possible that that might be easier even without Gdb involved and just using the grub command line, because grub already has I/O read-write commands. We just get less scriptability that way. Like, I can imagine writing a Python script that runs on the Raspberry Pi that just sends grub commands over the serial port and automates that. But it might be more useful just in general to have some Python and Gdb support here, and then we could use that to do I/O also. We just might need to like assemble a tiny code fragment to do the job. Let's make those windows overlap a little less. Not always helpful that these terminals have different sizes. Yeah, so from several of the previous streams, I have this little Docker build system to make the images for this, and none of the grub stuff has changed in there since last time. I just changed some of the config files. All right. So then the way we have to actually connect this is I'm just doing this on a Raspberry Pi just since electrically it was convenient rather than something that's like grounded to the entire AV setup. And then this is just the Gdb multi-arch from Raspbian's repo. Nothing special going on here. And then this does detect the architecture correctly. Yeah. So then I can just do target remote debug. And the baud rate should already be set up right. So then it's connected. So we already have symbols for the what they call the kernel, which is really the module loader and the rescue shell for GDB, or for grub. I got those two backwards in last stream a couple times, I realized, calling grub GDB and GDB grub. Grub has a module loader. Grub is basically a little operating system, and the kernel loads at a static address, but everything else loads at a base address that's determined at runtime, and there's a linked list we can walk to find all the modules. I should look to go back in. indecisive little boy. Might also be worth looking into those scripts that were packaged. There was at least one GDB script that I kind of glossed over earlier because it looked like it was mostly working by hooking the dynamic loader, but it's quite possible that they also have some support for like looping over the existing modules, and maybe we can adapt that to work in this environment instead of like whatever their debug environment was. Tuco really wants attention right now. Gosh. Cat butt. Anyway, on the last stream, I was doing a lot of like adding grub-related symbols to GDB. As I was saying, this thing I want to debug right now, though, is actually the CPU registers. As far as I'm aware, GDB does not have... Well, actually, I know... Oh, Tuco, don't scratch up my monitor. What are you doing that for? Gosh. Yeah, I was reading the source code to their GDB stub earlier today, so if there were any like extensions to handle things like the GDT or the IDT or I don't know, what else were we running into? Basically, there aren't any extensions. It's just like very vanilla GDB stub protocol. So you can read and write registers, you can tell the CPU to run, you can trap exceptions, you can put it in single-stepping mode. There's not much to it. But that does mean it should be pretty resilient. Like, I was curious, like, what is the actual... like how far can you step if you attach the GDB stub and then just like literally just try to single step through the entire OS loading process? Like, where would you expect that to break? And I think the answer is that it breaks when the relocator switches interrupt descriptor tables, since the GDB stub does need to have like the real IDT hooked in order to gain control when there's a debug trap. So I think what would happen is as soon as you replace the IDT, you all of a sudden have no debug trap handler. And assuming there was still going to be a reason to stop, like if you were single stepping or if there's a breakpoint, as soon as you would have stopped in the debugger, instead you just crash because you hit a debug handler that isn't actually assigned, and some default handler crashes on your behalf. Tuco is very purring right now. Oops. Bad aim on that button sometimes. Oh, that's a good question from chat, whether the stub runs in real mode. It runs in protected mode, but the thing is, like, you're accessing it through a trap in the CPU, so I think the CPU will switch modes back into protected mode to go into the debugger. So I don't know if the debugger works in real mode code, but I haven't ruled it out yet. It seems like the debugger might support real mode, but it's written itself in protected mode. Most of GDB is in 32-bit. There are just bits and pieces in 16-bit. Like there's some relocator code that's in 16-bit. There are some trampolines they use to go back and forth between real mode and protected mode. And then of course there's the boot sector. Grub does go back into real mode to make calls into the BIOS to use the BIOS disk routines by default. Oh. scratching at the screen earlier. That was not good. I guess we could try the same exercise in a virtual machine, like basically doing the same stepping through the relocator and verify that it doesn't actually crash in the same spot. That might be interesting. Yeah, man, x86 processor modes are quite a field of overgrown weeds at this point. You can do some really strange stuff between 16-bit and 32-bit modes too, because even after you set up parts of the CPU that are kind of new to the 32-bit x86 era, you end up you can still run 16-bit code. So you can do all these variants of what some people call like Unreal mode, where you set up the CPU so that you can still access more than a megabyte of memory, but you're running 16-bit code technically. And a lot of it's weird because of the way x86 itself like repurposed the meanings of like what a segment register is between 16-bit and 32-bit. Because in 16-bit land, you had these segment registers that were used to extend your addresses so that instead of just 16 bits, you could actually reach an entire 20 bits of addresses. And there was a lot of redundancy there. It was just you shift the address over by 4 bits and then add it to the other address. But then when 32-bit and protected mode came along, now we have this entire lookup table machinery where the segment is actually a table entry instead of just an offset that gets added to your memory times 16. And so you can set up different combinations of that where maybe you're running code that expected it to be in regular 16-bit mode, but it's actually got access to a different memory environment. And then there's also this actual, like, basically like a virtual machine that you can set up to run 8086 inside, like a 386, like virtual 8086 mode, which used to be common for things like DOS emulators, but nobody uses it anymore because 64-bit CPUs dropped compatibility for it. It used to be used for DOS emulators and also for things you might not expect, like video drivers, since, maybe not so much anymore, but it used to be fairly common that if you wanted to initialize a video card in a vendor-independent sort of way, the way you would do that is by running its video BIOS, which is just some 16-bit code that's stuck in the ISA address space somewhere. It's normally run by your BIOS really early in boot so that you can actually set up the display and have something on the screen. So I think like x386/xorg actually still has a little 16-bit x86 interpreter that they can use to run those BIOSes if they need to. I hope it's deprecated. I wouldn't be surprised if it isn't, though. Tuco sure is purring. One of these addresses that I had issue with is this actual symbol that I'm seeing in the backtrace, this lcont. I still haven't looked at what that is, so maybe I'll do that now. Yeah, these are the two addresses. Tuco is so relaxing right now. He was a handful yesterday. Tuco. Here's the question, does Tuco purr? Yes. I don't know if you can hear him, but he's been purring kind of off and on. And GNU software is so funny sometimes. That's weird. This is just like normal looking startup code. I don't know why there'd be any dependency on this after boot. Oh, Tuco's just getting all melty. That's the symbol we're seeing over here. And then we've got grub main. Tuco is purring loud now. now both of us can relax. As I gulp more coffee. Oh man. Guess it would be useful to verify where the GDB stub resources are, just so I know I'm not stomping on that. So we have a grub Gdb IDT, and an IDT descriptor, and an original descriptor. Let's check those out. Oh, am I gonna take a detour to look at that module loading script, or am I just gonna keep doing this manually? I was saying I didn't want a career in grub debugging. Right, maybe this would just be a fun thing to try to get used to the Gdb Python integration. But this has probably already been written. Let's just see what's already here. Yeah, I think this does both. It looks like it both loads existing modules and hooks new modules. So I think we just want to make a slightly modified version of this. So this is a .in file because the build system was going to do something to it. Let's see if we've got the actually compiled version. Oh, it wouldn't have been in here, would it? Oh. Cool. Can we just run that? Yeah, I think we just need to modify this to have a different target. We can save our customization energy for like x86 IO stuff. So surprise numlock. Drum roll. Oh, did we actually disconnect this somehow? It is going to go back in a couple seconds. They might be out of sync now. Oh, there is no timeout actually. It's not going to retry automatically. Yeah, fine. Let's run that again. Do that. Okay. So we get some utilities now, like, ooh. Load all modules. Yeah, that's convenient. Okay. Almost like it was designed to be helpful. So now the thing that I actually wanted to do is just to look at the Gdb interrupt descriptor table. Yeah, so that's like approximately where I would have expected it to be. That says the interrupt vector table is up in vicinity of the Gdb module. What about the original one, though? I would expect this to be near the kernel, maybe. Oh, okay. Or it's in the traditional user mode location, or traditional real mode location, which is at the very beginning of memory. I don't even know if most of grub actually does a lot of interrupt-driven stuff. A lot of what I've seen so far from grub is stuff that is not interrupt-driven, but I don't know to what extent they use interrupts in grub. Interesting. And so I think if we looked at that table, we'd see a bunch of little trampoline functions that mostly just call the there's like a wrapper they define in here. Yeah, these are all up in one EE. Okay. So maybe it would be useful to reproduce one of these crashes from before with our current setup just to verify everything is still reproducible. I got these two different addresses depending on whether or not I tried to use the cutmem command to explicitly tell Gdb or tell grub to avoid the region right at 8,000. And I tried this one twice and got the same answer both times. I've only tried this one once, so let's try that one again. And so much easier to load symbols now. So what do we have in here anyway? Can I not complete the new commands that were defined? don't think you can use this to load symbols for a module until it's actually loaded. So I think I want to load the modules first. Oh, Gdb is picking this up right away. Oh, and it looks like relocator was a dependency of chain, so I really only had to load relocator there. Let's speed this There's a question, what am I working on? I'm trying to make this computer boot. Oh, that's not a good sign. We're gonna try that again. Gosh, okay. So, actually, I think that's what I want to do. And power cycle. It's timed out. I guess I have to boot it and then attach, or it will just time out. Am I having a baud rate problem? Or am I having a bump to the connector problem? Oh, I'm having a bump to the connector problem. Oh gosh. This is terrible. Is that actually working now? Okay. Gosh, okay. I still have to go into the command line. I think I can just run chain loader and let it load everything and then set a breakpoint. Yeah, this is convenient. Yeah. Okay, that's much better. Okay, same place we were at yesterday. This does a bunch of setup in C. These lines here are actually unpacking the CPU state out of this structure and putting it into some assembly code that's acting as a template for generated code that actually sets up the CPU state later. So I was doing like a break line 166. So that's the generated code that we've got. Okay, so then these are little generated mem copies effectively. And we had a crash inside this first one. That 828A. So I'm going to just run the same experiment. Buffer is full of character turns. Love to run Gdb over 115 kilobaud serial. Of course, they're copying memory a byte at a time. Oh, is that it? Yeah, that's reproducible. 828A. So, what could it be? How could we narrow that down? I mean, we could try some other ideas. My plan A for this stream was to look at the registers on the system on chip to see if it's configured in a way that would cause this. Well, so this should be really easy to reset now. Maybe we don't even need to. I mean, yeah, we must need to reset Gdb, right? Because modules are going to end up at different addresses. There certainly could be pointers to something in high memory. That's interesting. Could this be a descriptor table? Alright, this is where it would be useful if I could just assemble some code into memory. So maybe we should try doing that. Actually, I wonder if grub already has any commands that would show us like the descriptor table status. Like, where does grub usually keep its GDT? Do I have symbols for that? Yeah, I think that's just in the... That very well may be in low memory. I mean, it wouldn't make sense if we were just overwriting the GDT, because then grub wouldn't boot anywhere. But, you know, it'd be nice to know how this is supposed to work. gosh, so I don't know what's actually going on here, but that looks a lot like a memory descriptor table kind of shaped thing, and I'm suspicious that it might be writing over a descriptor table that's still in use somehow. That doesn't really make a lot of sense. I'm curious what happens if I just use a bigger cut num region though and cut out both of those. Like, where does it fail next? I think I could just use another clue there. Try one or two more kind of easy things like this, and then maybe try writing a tool in Gdb Python to dump the system on chip registers. Going all the way up to the first kilobyte there. I don't know if I can. I need a breakpoint now. Right, I mean, we should be doing all of this with interrupts off anyway. Like, that CLI is disabling everything that can be disabled, which does not include non-maskable interrupts like system management mode, but it would include things like timers and serial ports and whatever. And the debugger still works because it doesn't need interrupts. It does not include things like processor exceptions, which is why we're still getting breakpoints. Is that what's going on? Is this like an issue where we're intentionally like overriding some object? I'm not really sure what that would be, but some object that's required for normal interrupt handling. And then maybe even though the GDB stub itself is well out of the way, maybe it's depending on something that we're currently overriding here. It'd be great to just test this using a different like debug path, like maybe write over these same memory regions from the grub shell, maybe. Also, I wonder if, I don't know, there might just be different ways of like simulating a boot up in GDB to see where other problems are. It's possible that this problem is more of an artifact of the debug mechanism than it is like the actual problem, and there's maybe a separate problem that we're also going to hit. So maybe there's a way we can jump directly to that problem. So we are relocating this to a different address now. We're putting it up above that area we reserved with cutmem. So I don't know if this will fail or not. It might actually go through the whole thing, but maybe it'll fail somewhere else. Seems like we have way more viewers than usual on Twitch and fewer viewers than usual on YouTube. I wonder what's up with that. Anyway, welcome everyone. Actually, the YouTube counter is bouncing around a lot, so who even knows? Maybe everyone's leaving after 3 seconds. Oh, I got less than a page to go. Huh. This is interesting. This completely is just dodging the problem without understanding it, but like I was saying, that might let us get to a different problem, which is more illustrative of something we can work on. Welcome to anyone who's new here. I'm trying to get Linux to boot on a fairly strange computer. It's a 486 PC that is usually a voting machine. And at this point, I have it getting past the BIOS and into the bootloader. Well, into grub in this case, like after trying a couple different bootloaders. This is certainly not what it usually runs. The proprietary OS this usually runs has a really simple bootloader that looks a lot like a DOS bootloader. There's a question about whether this hardware is so obscure that no one's got booted or Linux booted on it before. I mean, it depends on what you mean by this hardware. I mean, fundamentally, this is just a 486. So, like, plenty of people have run Linux on 486s. But this exact board, I don't know if anybody's run Linux on this. I've definitely seen people run DOS on it. It runs DOS without too much fuss. I had some trouble with that, but that was mostly because of disk geometry issues. There's a question about how I got into this. This is Gdb running on a Raspberry Pi, so if you just install Gdb multi-arch, you can debug all sorts of platforms, including i386. And then the actual voting machine is running a grub image that I compiled. But you can also run this on a regular grub, it's just you might not actually have debug symbols that match. This is getting much further than it was before. Our only speeds here are extremely slow and far too fast to be useful. I think the closest I've seen to someone like repurposing this machine for a different application than the voting machine firmware it usually runs is some security researchers installed a DOS version of Pac-Man on it because that was something that they could get to run in the portrait mode screen orientation. But that's a lot of why I'm trying to get Linux on this, is I wanted to get it running a version of like Xorg that I can just rotate the screen on so I can get portrait mode working in more applications. This is really like we're playing chicken with the machine. Like, how far can we get before it'll crash? It's like watching paint dry, right? Except it's watching memcopy progress. Oh, is this the crash? Right as I was getting cocky. That might be it. Right, I mean, that's probably just fairly random at this point. Like, I wouldn't be surprised if this is reproducible every time we run it, but I don't know if this address is going to be extremely meaningful. Wait, there's a question. My main motivation is to play Pac-Man now? No, that wasn't me. That was a different researcher I was mentioning. That was somebody who was mostly investigating this as an insecure voting machine, and one of the things they did was they ran DOS on it in Pac-Man. But no, that wasn't me. Like, I tried running DOS on here earlier just as I was trying to get some other stuff working, but I mean, the highest level goal that I've mentioned so far on this is that I want to be able to use this as a prop for some videos and run some microcontroller programming software on it. There's a question about whether that PSOS embedded OS is based on DOS or if it's a complete OS of its own. It's not based on DOS. I just said it has some like DOS vibes in the bootloader. I think it uses the DOS MBR, and the volume boot record looks a little bit like DOS's, but like it's like its own 32-bit operating system. I don't know if it's related to anything else. The voting machines are ridiculous. Like, yes, they're not actually good at anything. They're just kind of a hilarious object. It's dark comedy. Interesting. Let's make a script that we can start editing and hacking on. Okay. I should put the Python in a separate file, probably. Or just tell my editor that this is a Python file. No? Oh, because we're not waiting for the debugger. Okay, cool. So that attaches the debugger and gives us a way to run some Python. Now we need a place to put some temporary code. So where can we do that on the system? Oh. I can just call malloc. That's great. This would be parse value. Is that it? parse and eval. Yeah, gosh, that is extremely handy. I guess I don't need to cast it to an int if I'm passing it back to GDB, probably. I don't know, I like int. Let's just allocate a 64K or something. Okay, can I define new commands from this? Let's just actually pull up the GDB documentation. There's a request for context. I'm trying to debug this machine that won't boot. It's crashing while I'm trying to boot. Hence the debugging grub. I guess I could read about these value objects. Are you not going to open my current location in the table of contents? No, but there's a button for that. Okay. Alright, so part of what's annoying about this is GDB doesn't, as far as I know, have a built-in assembler. We could use a number of external assemblers. There are assemblers in Python. I might just use NASM because it's handy. Values in Python. Oh yeah, inferior is what GDB calls the program you're debugging. Yeah, that's fine. All right, we'll just keep that as a value. That seems useful. An X method. I don't even know what that is. Interesting. commands in Python. That's what I want to do. I know I've seen variations on this before, like Python add-ons for GDB that let you assemble and run little programs. The ones that I've seen are targeted to like regular operating systems though. So I don't know if any of those like off the shelf would work in this environment, and it seems kind of fun to write one anyway. So we'll just be writing a little command for GDB in Python that takes a line of text, sends that line of text out to NASM to assemble it, and sticks it in memory. And that's probably all it'll do. Maybe we can have the same command or a variation of it also run the code by single stepping over the instruction. There's also a whole feature in GDB for compiling and loading C code. I'd be really surprised if that works without an operating system though. We might try that though. All right, the first failure it's hitting is that I just don't have a x86 compiler handy, but that's easy to fix. Gosh, when we could try this, if this works, it'd be super convenient. I just don't expect it to work in this environment. We might move this to an x86 machine. This is on a Raspberry Pi right now. All right, do these work? Tugo looks so comfy. There's a question about whether anything in memory is really safe if I'm getting this crash during relocation. Yeah, that's a good question. I mean, I still don't know what this is. It smells like a descriptor table, but I don't, like, that doesn't really add up. My impression is that stuff above a megabyte should be pretty safe, though. There's memory mapped I/O in the first, or in the top half of the first megabyte for legacy peripherals, and there's more memory mapped I/O, like probably way above actual DRAM. I don't know exactly where, for the video chip. The video chip is on Visa Local Bus. It uses some of the same address ranges that you'd see on PCI, but it's not PCI. These are all libraries. I'm not looking for a library here. This is like the opposite of what anybody ever wants to do, is compile for i386 on a Raspberry Pi. I might just have to move this to a different computer. Do I want to move this? I guess so. All right. Does this reach? It's not going to reach. Oh gosh, this is fragile. Tape it to the table. Just gotta not mess with my KVM switch, because this goes through the KVM switch. Okay. Abandoning Raspberry Pi, going back to full-on PC. Okay, got all the files copied off the Raspberry. Can we just run this then? Do I not have Gdb installed on this machine? Oh no. It's a tragedy. I'm like, why is it doing grub stuff? Oh wait, this machine also runs grub. Oh. I would need to give myself permission to the serial port. Oh. Are we still connected? I should see if we're having signal integrity problems on this. Connecting it directly to this computer is much more electrically complicated than going to the Raspberry. I wonder if it's serial baud rate. There's the baud rate. Cool. Not a signal integrity problem. Now we've got a cute O-scope display output. All right, so we have a slightly nicer setup. Let's see if we can compile code then. Compile. What can we do? How about nothing? Okay. mmap 64. Are you sure you need that? I think the GDB manual has that. Where did I put the GDB manual? I guess we can turn the scope off. Do we try to make this compile thing work? I think maybe we're searching the source code for GDB instead of the manual. Do I not have the GDB source code? That mmap is not coming from the wrapper, right? That's coming from the loader. Like, I doubt this is something I can override without recompiling GDB. Do I not have NASM? I don't care about the load address, right? I'm just going to make all this relocatable, like whatever. I'm like feeling lazy enough that maybe I'll start by just writing a program that's special purpose just for IO outs. I guess outs and ins. Actually, what do I specifically want to do is read the registers from the system on chip. That's down here. Do you know that they insist on calling this a microcontroller? It's a 486 compatible CPU, but it's on one chip, so it's a microcontroller. It doesn't include RAM though, so I mean, I guess they must be counting cache. So this is a cool tidbit that I had forgotten about. This system on chip does actually include a standard, what is this, 82365 compatible PC card controller. So I had forgotten about that. I don't know if that's wired up in a standard way, but that means it's much more likely that maybe we can actually find a driver configuration that works with these PC card slots on the board. So these indexed registers. So this table, this book has like a few big sections. It has all the direct mapped registers, and then it has the different sets of indexed registers. Right. So we just want a function that lets us put an arbitrary value into 3 and then read back, or into 2 and then read back from 2.3. Oh, and we don't need to write a move instruction for this, right? Because we can just set the register status, or we can just set the register contents. Oh, right, this is Intel syntax. Do I need a literal specifier or a memory access specifier? Okay. That should be right. So we can stick this in memory and run it. It's probably easier if we do just like shell out to NASM instead of having to like copy this by hand. That's right. So we established that NASM works in a pipe. We could try a less old assembler. Or we could just deal with temporary files. Does Python have a nice way to do temporary files these days? think I want a temporary directory. That's cool. Shouldn't I be using with for that? I forget how that works. Oh, not like that. Like literally the word with. Oh my gosh. I still kind of have a case of Python 2 brain. Do I need to encode these strings? I feel like I probably need to encode the strings, but I don't know. I'm not going to bother with an org. Python just defaults to Python 3. It's so nice. Let's just test this piece. I need to call like dash or .name or something, right? Is that not actually how you do this anymore? Oops. Oh. Yay. We can assemble things. It should work for blocks of code too. Not into the shell, thanks. Let's also move that. Cool. Okay, I think we have a thing. So we can assemble stuff. We need a way to stick data in memory. Oh, Gdb manual, where did you go? can I define a value that's like a block of memory I'm managing? I mean, at the underlying Gdb protocol level, I think I'm always just like stuffing individual 32-bit words into memory. Program spaces are what they call memory, I guess. Maybe that is just loaded program code, though. I was expecting there'd just be a section about manipulating memory. Cool, so that works inside Gdb just fine. These are objects or methods on this inferior object. That's right, because Gdb can't make those global, because in a lot of cases it could be managing multiple threads, which usually have the same view of memory but don't necessarily have to. Okay, so I want gdb.selected inferior. Oh, I can just pass an entire byte buffer. Great. At least I hope this supports bytes. This documentation might not have been updated for Python 3. Okay, can I disassemble that buffer? I could actually put this buffer in like the namespace so that I can access it simply. Right, I need this to be 32-bit code, not 16-bit. We're just gonna keep allocating memory. Yeah. Okay. So I'm sure there are a million different ways of setting the registers. The lazy way is using like gdb.execute. I should put this stuff in a command though, right? Let's figure out how to make a command. Okay. A very small hello world example there. Trying to decide how much granularity to break this down into. It would be cool to have a command for actually running arbitrary assembly code. And I kind of just to start with want a command I can use just to sort of trigger this whole thing and read a value in from the system on chip registers. Calling super like that. Has Python super also changed since I really looked at this last? Method resolution order. Yeah, I don't know why I can't just call super without any qualification there. I'm gonna try that and find out. Find out why not to do it. What is that then? Command user? Is that just the command section? Let's try that. Oh, that's right. I needed to instantiate this class too. Can I do that now? Oh, cool. That does share the same namespace. Okay. Nice. And just keep allocating memory. Okay, so if I actually wanted to run this code, oops. So we can write this code and load it once, and then loop over the addresses. Does GDB know about byte-wide registers? Oh, right. Percent is the GNU assembler syntax, not the GDB syntax. There's got to be a nicer way to do that, right? Let's just see what this does. Oh. Needs a little work, but it's not completely failing. I guess I actually want to cast this to unsigned. Oh. There was a comment about it being open rather than file in Python. So Python has both. I don't know what they did with file, but you can also call the constructor on the file object to open a file. And I thought that that's what they were moving to with Python 3, but I don't think that actually happened. This is mostly that I haven't written a ton of Python since they were doing a bunch of really awkward Python 3 transition stuff. Why did that power off? And there's a question about a microcontroller that this board doesn't have, so I don't know what the question is about. All right, this would be a little easier to read if it actually aggregated them all and then displayed them at once, but this is basically it. This would be much faster if we weren't like going back and forth between GDB and the target all the time. So it might make sense to just write a little assembly fragment that dumps all the registers. It's a little worrying that some of these have the same number coming in. Like, I would expect to see that if the bus actually wasn't quite fast enough and that was still the old value. So maybe I'll add a delay. I don't know. Let's have a buffer. Oh, how does this work? Something vaguely like that. That's a little simpler, right? No more looping in GDB. This wouldn't still be here, would it? No. Lowercase n. Oh. I was just trying to comment my code, gosh. What is the NASM syntax for that? I mean, it's the same as the Intel syntax. Go to the real documentation here. Why do I not have that on this machine? Dragging out the Bible here. this is just going to tell me it works with like all the addressing modes. Okay, those are all the addressing modes. What was I trying to do again? That's right, I can't do that directly. I thought I could do that in one instruction. Whatever. Can you move from EIP to EDI? How about that? Does it just want IP here and not EIP? Oh gosh, I don't want to log into GitHub, thanks. Like, when I usually see position independent code, it's doing like a push pop to get at that, but I thought there was a better way. There should be an addressing mode for that. I'm just using the wrong syntax in ASM, right? It doesn't want RIP, does it? Like, this is not 64-bit code. 32-bit position independent library that can disassemble like grub itself, maybe. Actually, I want to actually use NASM syntax here. Right, are they keeping a base pointer in EBP for most of those? Or is that's just the stack, right? Where is the actual position independent code? I could just put this temporary buffer on the stack. I just didn't want to use the stack. Like, do we want to do a call and pop? Is that the way to do this? Yeah, I don't know. It's been a while since I had to think about 32-bit x86. I guess there's no direct way to read EIP, and we just do something different. Oh, did that actually assemble? Oh, interesting. We have some context that apparently at some point in Python 2, they started encouraging calling the file constructor, and then they completely backpedaled on that. Yeah, serves me right for having an out-of-date memory. Ooh. That's the wrong width, but, yeah. It's B, right, for byte. I bet this looks interesting on the O-scope. Okay, oops, stay on that channel. So there's the GDB stub polling the serial port for bytes. There's GDB connecting. I want B and X though, right? Yeah. Oops. Cool. So each time I'm doing this, I'm using a fresh block of memory because I never actually freed the memory I was using. This looks consistent. It'd be cool if this was at a nicer round number though, right? We can do that. Oh, some folks thought I was trying to go for the stack instead of the instruction pointer. No, I was trying to write it in memory right after the code buffer. Yeah, now we're lined up. Why did we reuse the address? Am I actually freeing that memory? Yeah, I don't know about that. I was expecting that to get a new buffer each time. It's a little concerning that the address is the same. Oh, there's a request for context. I'm trying to make this machine boot, and I'm debugging grub with Gdb. You can see the machine right there. This sure seems like it's allocating a buffer that's too small. Does grub malloc take any other arguments, maybe? No, it looks like a normal malloc. Yeah, what's up with that? I'm trying to malloc 64 kilobytes, and it's giving me significantly less than that. Like maybe 64 bytes. Are we gonna have to briefly look into how malloc works just to see if this is even sensible? Okay, so we have a grub base. Grub real malloc. Oh, so right at that 1 megabyte boundary is the list head for our memory manager. Is this just never gonna fail? Really? I must not be sending this parameter correctly, right? Can we step through something that we're calling from the debugger? Evaluation of the expression will be abandoned. That's fine. That's actually what I wanted. What if I... I wasn't expecting to have to debug malloc here. I'm wondering if there's a limitation on how large a chunk of memory this is intended to be able to handle. I mean, this looks like it's intended to be able to handle up to 1 megabyte. Oh, address space size minus 1 megabyte. Yes. This is just checking the top end then. My suspicion here is that GDB is not successfully calling malloc. I think maybe the argument is something like OX20 instead of whatever I'm sending, but I need to use the restroom. I'll be right back. I might even get some more coffee. kind of tempted to leave malloc alone and just choose a memory address that I know no one else is going to be bothering with. I guess we could also turn on debugging, and we should be able to trigger some malloc debugging with this. That might be nice, actually. Let's try that. Alright, I cannot continue after this point because I didn't save and restore the CPU state. That's something else I should do. Maybe I'll do this slightly differently. Was my camera overheating again? Also just make this a C callable function, right? And then just use the call functionality, except I don't even know if I can trust that because it's giving me suspicious results from invoking malloc. Whoa, hey Tuco. Hey Tuco. You'd think the Gdb Python would have some sensible way to save all the register state. Tuco. Oh gosh, Tuke. There's a question about how I injected the GDB stub. I didn't. It's part of grub. For anyone who hasn't used the GDB stub, though, they're pretty simple. Like, you can include a GDB stub in most projects. In this case, it's not even using interrupt-driven serial port I/O. It's doing polling serial port I/O, and it has an interrupt handler for the processor traps. And there's a request for context. I'm still debugging grub to try to see why it isn't booting. And I was going into a little tangent here to make a tool to dump out the registers on the system on chip. which is probably working, and I want to look at those registers in a sec. I'm just also getting distracted by malloc acting weirdly, and so I'm doubting that I can call functions in GDB successfully here. I think there might be a calling convention issue, because it doesn't seem like grub malloc is getting the right argument. It looks like it's allocating more like 32 bytes of memory, and I'm trying to allocate 64K. And yeah, it's possible that it's getting a 0. It's possible that it's getting, just like some garbage, or it's not getting the value set at all. It's some variety of calling convention problem, probably. Registers. I think I need a frame object for this. I don't know, I feel like I could go pretty deep in trying to make this work really nicely in Python, or in Python and GDB, but I could also just kind of make this hacky and move on with my experiment. Let's put this... It's tempting to clear memory too. Maybe I'll clear memory myself. I just want some extra assurance that these aren't old values I'm seeing ever. Tuco, you're kind of in the way. I was hoping to keep AX clear, but whatever. So I want to clear twice the length of the memory I'm actually using with a pattern that I can notice easily. So EIP for the code buffer and EAX for the data buffer. Connect this. Oh, Tuco. Kitty. There we go. Oh. Oh, what was I doing there? I think that's fine. I have loop count, port number, and a destination pointer. looks right. So I have some more confidence now that this is running and not unintentionally sharing memory with parts of grub. We could also try to make this actually save and restore state. I don't think this is gonna... Well, I don't know. This is gonna be a little dirty, but I saved and restored most of the registers just on the stack here in this code. And maybe I'll just save and restore EIP and EAX manually. I'm sure there are 100 better ways of doing this, but whatever. Need to reboot this. Okay, so where are we here? Someplace, whatever. This is a grub-specific Gdb script that I'm using to add symbols for all the current dynamically loaded grub modules. I've got a nice backtrace. So let's see if we can move in and out of the debugger. So grub command line. Cool, we can go back and forth. Let's see if we can dump the registers now. And continue. Haha. Yes, okay. That's what I wanted. Okay, so I don't expect expect any of these to change while we're in Gdb, because Gdb doesn't know anything about this hardware. I think now the thing to do is to go open up the CPU manual and see what all this means. Maybe check in this script, because I think this script is actually useful now. I might be able to reconnect if I do a gdb stub break. It might be too late though. Ooh. Oh no, that worked. Nice. Reconnecting even. Cool. Okay, so we can also use the low 8 bits of the address as our index into this register map. Okay, DRAM configuration. I don't super care about the DRAM configuration. I guess we could see which of these are enabled. So we have a DRAM bank 0. No DRAM bank 1. It's weird that type would be set even though it's not enabled, if I'm reading that right. So it looks like 2 DRAM banks enabled, 2 DRAM banks disabled. DRAM refresh control. Does that make any sense? Oh yeah, that's in self-refresh mode. Yeah, refresh enable, timeout disabled, self-refresh. Okay. These are making sense so far. Like, I don't really care about the DRAM. I think the DRAM is probably fine, but, you know, just like where I can, cross-checking between what I'm seeing and what I expect lets me know that my tool is working. Drive strength. Yeah, so I can skip a lot of this stuff. Oh, memory windows would be useful to know about. Non-cacheable memory window. That's interesting. If I'm reading this right, this means that there's a non-cacheable memory window right at 8,000 hex, which is in the vicinity of where weird things were happening. Okay, is this where we find out about system management mode? This is index 11. Oh. Sorry, I'm reading this wrong. I was reading here as if I was at 0x10. So no, we are down here. That is the non-cached memory window. I guess that means the window is at 0. I don't even know if it's enabled, so it's quite possible it's disabled. That makes more sense. Now this is the SMM and it's all 0. This doesn't tell us if we have SMM, it just has some options for SMM. Some more non-cacheable stuff. Yeah, and this confirms the non-cacheable window is disabled. Okay. Oh, there are several non-cacheable windows. Okay, window 1 is also disabled. This byte 9 is at 1.4. Cache and VL miscellaneous. That is Visa Local Bus enabled, which is where our graphics controller is. And CPU cache write back. Interesting. And the rest of these are off. Okay. Pin strap status. Did we have a discontinuity there? Oh. That's cool. I think these sections where we're getting these incrementing numbers, those are probably actually open bus slots where those registers weren't implemented, so we might just be getting a copy of the address. So it looks like we have this 9 at address 14, and then I think these are unimplemented bytes at 15, 16, 17. All of these are unimplemented actually, so same pattern continues. And then we get another implemented byte at 0x20. So this is telling us, so pin straps are like pins on the chip that are intended to be set a particular way to indicate how the board is configured. So this is actually pretty useful. This is B, so we have bits 3, 1, and 0. This means our ROM is 32 bits wide. An external buffer control signal. Yeah, I don't know what that would be used for. Presumably the memory card interface. Oh, ROM shadow register. I think this is where the BIOS is hooked up. Oh. So no caching. This is also a cool feature, right? Redirect ROM chip select 1 to PC card socket A. I don't know if it's easy to use on this board, but the chip has a feature that seems designed to make it easy to debug your BIOS by moving the BIOS temporarily to one of the PCMCIA slots. I don't see much other ways to debug the BIOS, so it's probably helpful. And so no shadowing. We just have these 3 segment enables. So yeah, everything from C0000 up to right before F0000 goes to the ROM. That's where you'd expect to see the BIOS on the video ROM. This middle section, I think, is where they put the their OS initialization stub thing that you see when it boots every time, which does basically nothing. It's a giant empty space in the BIOS. Okay, 22. This is 0. So this is all defaults. No caching, no write protect. This one is 6. We have a reserved bit set, do we? No. We just have data size. This is, again, setting up the ROM for 32 bits. So yeah, this is set by the pin strap, but you can override it if you want. Okay. We have a 4 at 24. This is wait states for the ROM. It looks like we have 4 wait states. That's interesting. Is our BIOS ROM really that slow? Okay, now we're on to ROM chip select 1. I don't know if this is actually connected to anything. Looks like not. So 5, 6, 7 are all zeros. Yeah, ROM chip select 1 and chip select 2 seem to not be connected. Okay, and then we have a bunch of unimplemented address between 28 and 30. So there's 28, and all of these are just displaying that open bus pattern, and then 30 is 0. So these are the MMS windows. This is a chip-specific memory management feature where it's not like a completely general purpose memory mapping thing, but there are a small number of hardware windows that you can set up to stick memory mapped I/O at a particular place or do cache control. This is the thing that I used a while ago to dump the BIOS, since there are some legacy mappings for BIOS, but you can also just enable kind of an arbitrary window using these MMS, and so that's how I grabbed the whole chip. So these are all zeros. 31, this is set. MMSD device. So these are all defaulting to ROMCS0, which is the BIOS. But 40. That is setting MMSF to ROM chip select 1. That is interesting. I don't know if that's actually used for anything. I'm guessing it's something the BIOS set up intentionally. So this means that maybe they're using MMSF for something. Now we've got some destination registers. So these are all zeros up until 3.6, which looks unimplemented. And these are destination registers, so these would actually have addresses if these were being used. Yeah, and then 6 and 7 are unimplemented. So it looks like the MMS windows might be used at some point, but they don't seem to be in use right now, like after the system boots. I would be surprised if the BIOS has any idea how to configure the PC card slots. They probably would just ignore those completely in the BIOS and have a driver in their PSOS application thing. So 38 pinmux. This is all defaults. These are all set up as GPIOs. Oh wait, no, I was reading the wrong row. 38. These are not set up as GPIOs. We have a clock output. That's kind of cool. I wonder what that's being used for. And okay, this is the 16-bit I/O chip select, so that's pretty normal. And all these are on. Yeah, so okay, all these pins that could either be GPIOs or ISA bus are being used for ISA bus. Okay, 6D. PC power. Oh, cool. They are using the PC card power control signals, which is a point in the column for this might be a standard PC card controller. It is quite possible that a regular PC MCIA driver would know how to operate this board's slots at this point. Uh, 6D. Keyboard column and row select. Oh. I hadn't actually looked to see where the keyboard was connected, but I had been assuming the keyboard was connected to the Super I/O chip because that's where most of the 5-volt I/O is happening. But it looks like they have XT keyboard pins enabled here. That's a little surprising. And they chose PC card signals instead of parallel port signals here, which is also what I would expect. Okay, this one's 2. This is selecting between programmable IRQs and keyboard matrix, and they chose the IRQs, which is expected. And they chose the GPIO here instead of this extra PC card signal, which is interesting. This is all ones, which is default. All the pull-ups are enabled. A few more Fs. Some more pull-ups and pull-downs. Yeah, that goes up to 3E, and then we have an unimplemented byte at 3F. And 40. What is 40? PMU force mode. Graphics controller enabled in standby. No, that's not it. Enable hyperspeed mode. I think hyperspeed mode is 66 megahertz. Yeah, we are in hyperspeed mode and hyperspeed mode. Okay, so that whole byte is just about the speed mode. Last mode. This is 1. This is also hyperspeed mode. This is just more about like transitions between modes. Timers. This one is 0, which is the default. Both of these timers are disabled. This is also 0, which is the default. Disabled standby timers. Got a couple more zeros here. Yeah, these are all just power management timers we're not using. And then 6 and 7 look unimplemented. Okay, and we have unimplemented all the way through 48 through 50. And then 50 looks like the next one. Suspend reset pin. This is all defaults. Rising edge, suspend resume. Disabled, so we don't actually have an external suspend resume pin. Yeah, I think they chose to basically just roll their own power management instead of making it compatible with whatever power modes the system on chip supports. They don't seem to have any like granular low power in this system. It's basically just full blast and completely off. Five one is unimplemented, yeah. And then wake up source at 5.2, all defaults, no wake up sources. Don't step on the screen, honey. Oh, did he switch channels on my KVM? Yes. Tuco is curled around my KVM switch. She looks so comfortable. Okay, more wake up sources set to 0. Do not wake up the system. All these are 0 up past 58. Lots of disabled wake-up sources. You would expect to have this many wake-up sources on something designed for like industrial controllers. Oh, camera keeps overheating. I'm gonna reboot the camera, but it's pretty warm right now. I don't know what's up with the past tense wake up bits. Like, these are actually about waking up in the future, not in the past. Maybe they just wanted to make a joke, although this document's pretty old. Okay, B, and then we have unimplemented, and then 60. Oh, why did this stop at 60? I've got like a hexadecimal problem, don't I? Oh yeah, this, I was thinking in hex when I wrote this. But Gdb is parsing it in decimal. Oh, do I have to do this again? Blah, fine. I'm not starting over, of course. I just need to get a new connection to finish. Oh, because Tuco stepped on my KVM switch. Right. Gosh. As I said, this is hazardous because the serial port is going through the KVM switch right now. Yeah, let's see if we can get TTY USB 0 back. All right. Oh, this is not even the right spot, is it? Okay. I don't think it likes being run from inside that SU where I changed group IDs. Maybe that's actually a communication error. I think my watchdog timer code is failing occasionally. Welcome to the grub. Will you connect now? Oh, is this? This has got to be the baud rate again, because I didn't actually set that persistently, and when Tuco disconnected it, sigh. Serial baud, is that all it is? Okay, that's better. Thanks, Tuco, for testing my code. So C-regs. Where were we? Okay, more registers. That is much better. So we were looking at wake-up sources around 5B. Okay, that was the last wake-up source register. And then we have some unused, and then 60. We have a whole row of zeros here. CS activity. I think these are programmable chip selects. I guess none of them are being used. That's actually a little surprising, because I figured they would have been actually pretty useful. So maybe instead of using the system on chips programmable chip selects, they're doing all the decoding on that lattice PLD that was over underneath one of the PC card sockets. CS activity. Yeah, these are like write to clear, like latches that you would use to see if there was any activity, which is interesting. More activity sources that are all disabled. I think these are used for the automatic suspend timers, which are turned off. Activity sources. Okay, so we had activity stuff all the way through 6D. And then 6E and F are unimplemented. 7D is battery/AC pins. These are all zeros. Oh yeah, this is a hardware feature I was reading about where you can have like a hardware low battery indicator that automatically throttles down the CPU speed, but they're not using that feature. This is why I was curious if the power management board, when I was looking at it earlier, would have had some logic for detecting like discrete digital battery levels. But I think their entire battery gauge system is done through an A to D converter, so they can read battery voltages, but they're not going to get any low-level signals to the CPU when the battery crosses a certain threshold. So we finally have a non-zero value at 72. BL0 state. So this is one of the battery level inputs. I guess we at least have a bit indicated about. We could try to see whether this changes. I just only have one power source connected. Yeah, so right now my power supply is pretending to be a battery rather than pretending to be the AC state, and I bet we would see this read differently if I hooked the power up to the other input. Assuming that's actually connected properly. Okay, and then we have unimplemented for 7.3 through 7F, which is what we see. Then we've got something at 6, or at C6, or at 80 rather, that is C6. Clock speed. Clock multiplied mode. Is that the reserved mode? I wonder if this isn't set properly because they never use high-speed mode, only hyperspeed mode. Anyway, yeah, 66 megahertz is what we're expecting here. 8.1. Clock auto slowdowns disabled. 8.2 clock control. 4 megahertz DMA clock. And PLLs enabled and suspend. Not super meaningful. Clock IO pins. 0. UART clock. I don't know if any external hardware is using this. They probably just use it for the PC104 port. Okay, then we have some more unimplemented registers. Eight is the factory debug register, so who knows what this is. It's read-write. They're just not going to tell us what any of this is for. That's fine. Another factory debug register. I wonder if that's like another value index pair. It's probably just a regular register. Anyway, then we have some unimplementeds until 90. And this is an SMI-NMI enable register. And it looks like these are disabled. This was one of the things that I thought might have been contributing to the weirdness, is if we had SMIs or NMIs going on. Looks like maybe not, though. So more NMI enables. All right, all of these are NMI enables, and they're all zeros. NMI is a non-maskable interrupt. It's something that could still happen and cause BIOS code to run even when we are trying to have all the interrupts turned off. It's a good theoretical chaos source, right? Like the hypothetical compiler bug. Oh, and this is selecting between system management interrupts and regular non-maskable interrupts. So these should all be inapplicable. So we have zeros all the way up through 9D. All that's disabled. Master NMI enable, master SMI enable. These are both disabled. That byte. Or no, 89 A, B, C, D, this byte. So 2 unimplemented. Now we have A0, a bunch of zeros there. This is more GPIO assignment stuff. A primary activity and wake up enable. It's like more suspend resume stuff that we don't actually need. So this is all 0 up until 8.6 or A6. Some more GPIO configuration. I guess you have to set the GPIO direction here. That's kind of handy. So far, these have all been inputs. I think these two might actually just be the GPIO values. I bet those values change if we toggle the switches on the front of the machine. We can try that later. So those 4 values are all GPIOs. Some more PMU mode change stuff. All these PMU mode change registers are 0. That defaults to 1. These are disabled. What even is that? GPIO PMU to chip select map register. This is like stealing a pin from a different subsystem. Those are disabled anyway. NMI mapping, so this should all be irrelevant since all of our NMIs are disabled. This is in its default value. More defaults. What is this? Ow, this is setting up the chip selects. So these are disabled. Maybe other chip selects are being used. Those are disabled. Oh, this camera's being warm. Chip select A. So these are now address registers, but they're all still zeros. In fact, we've got zeros from here all the way until BE and BF, which look to be unimplemented. Still kind of surprised they don't seem to be using this feature. Okay, all that's been zero. BD. Okay, now we have the two unimplementeds, and then C0 is keyboard configuration register A. Hey, sleepy cat. This is all set to defaults. This is not default. What is that? C108. Interface select 2. Okay. This answers my keyboard question. So I don't know why they had the pin mux set up to enable those XT keyboard pins. It might be that there are other pin muxes that cause those bits not to have any effect. But this is the setting that I think tells us for sure that the keyboard controller is in the Super I/O, because this is telling it to send the I/O accesses for the keyboard controller out to the external bus instead of handling them internally. So this is going to be something the BIOS set up intentionally. Keyboard input buffer. That is for implementing emulated keyboard controllers, which we are apparently not doing. Same for mouse. Keyboard status register, write register. I think that's just going to be whatever was written to this last, which was 8 here. keyboard timer, keyboard column. This is like a special purpose GPIO, which, I mean, it's like, obviously it's not GPIO if it's special purpose, but like, this is like a very generic output parallel port, but it's for setting the keyboard row and column. Similar deal with this byte. We're not using the keyboard matrix driver, so all this is irrelevant. Keyboard row register B. Termination control for the keyboard. Huh. Oh, and then we have a bunch of unimplemented up until D0. Internal I/O device disable / echo zbus configuration register. What? Oh. Internal I/O device accesses will be echoed to the ISA bus when this is set. So that is disabled. Is that a PC card controller? Yeah, okay, the PC card controller is enabled. Cool. Oh, and these are active low, so the DMA channels are enabled. So DMA is enabled. Internal I/O accesses like these very ones are not going to the external bus. And the PC card controller is turned on. That's cool. We should definitely try adding a PC card driver to this Linux kernel, since we might be able to get Ethernet if I can just eBay an old Ethernet PC card for this machine or something. Oh, and that's an RTC disable. Interesting. So yeah, I think we're using the RTC is another piece of hardware like the keyboard where we have one on the Super I/O chip and one on the main system on chip, and I think we're using the system on chip's RTC. Oh yeah, I bet MMS window F is for the PC card controller. They don't seem to be using the MMS windows for BIOS. Port configuration, D1. We have a serial port enabled. So this is the serial port they use for the touchscreen controller, and then the parallel port's disabled because we don't have pins mapped for that. Parallel port configuration register is all disabled. UART FIFO control shadow register. We just have the reserved bit set. I don't know what that's about. Interrupt configuration register A. This is like, I think this is interrupt routing that would be used for the PC card slot. These are just interrupt assignments. I don't really care about that right now, but that might be interesting later if we're trying to have a driver for that. So yeah, all these are interrupt assignments. This is one interrupt per nibble. Oh, and this is interrupts also. Okay, now DMA channels. Got some mapping set there on DMA channel 0. Internal graphics control, which should be disabled. Yes. Internal graphics controller is disabled. More internal graphics controller. Okay, and then DF is unattached. EO. Write protected system memory window. Seems to be disabled though. Overlapping ISA Windows start address. These are intriguing but disabled. Suspend pins, also zeroed. More suspend pins. IRDA. Did we skip a couple? Yeah, so E6 and E7 are unimplemented. Oh, and E8, E9. And then EA is IRDA. There was an interesting tidbit that the datasheet pointed out that there are actually separate physical pins, I think. I think there's just one UART, but there are always separate drivers for the IRDA and like regular RS-232. Anyway, it basically, I think, implied that no matter how they configured this, there would still be some dedicated IRDA pins. So we could probably find those and hook something up to it if we really wanted an additional serial port. An additional shared serial port, really. I don't think IRDA actually is disabled. I don't think it needs to be disabled specifically. I think it's just not being used. Oh, here we go. UART versus IRDA. That's it then. So yeah, you'd have to temporarily borrow the UART. IRDA status. Receive FIFO empty, transmit FIFO empty. IRDA CRC support. Interesting. So it's got some protocol support there. Okay, so up to EF was IRDA stuff. What is FO? PC card extended features. Force card detect event. Yeah, none of this is being used. Standard or enhanced mode? We are in standard mode. Not sure what that is. This is default. We have pull-up resistors enabled on both sockets. Bunch of unimplemented. Oh wait. Yeah, no, that was F2. Unimplemented up until FF, which is the revision. I don't know why it says default 00 here. We apparently have a revision 0.3 chip. Well, that was all the CPU's, what did they call this space? Setup and control indexed register space. So we know there is no system management mode, there are no weird memory holes or weird mappings. Whatever we're seeing is just regular software. And I'm guessing at this point the BIOS isn't involved, since we shouldn't have any NMIs or SMIs happening, and regular interrupts were disabled during that crash. So my assumption at this point is still that the crash was caused by some interaction between what we were doing and Gdb itself, rather than something weird about the actual system here. It's a bit disappointing because I was hoping we'd find a lead there, but that basically just confirms that a bunch of things were not the problem, and I'm still not sure what the problem is. So we could switch to a different approach. Instead of trying to step through this or trying to understand this particular crash, we could try an approach where we just add a bunch of additional lower level debugging to Gdb and then try running the chain loader normally. There's a lot of ways we could do that. Like we could have some extremely low level serial port debugging by just poking values into the serial port registers. We could do IO port debugging out the ISA bus, which would be a little faster. Yeah, IRDA is pretty nostalgic, right? Did anybody ever get that working? I used to have a Palm Pilot with IRDA, but I don't think I knew anybody else that had a device. I think one time I ran into somebody with a Palm Pilot and we tried sending a file, but I don't think we had enough time to get it working. That was a nice little Python thing that we put together, though. That's going to be useful for maybe other things. Oh yeah, I wanted to look at the Gpios maybe while we're here. Is this still connected? Oh, Tuco is laying on my keyboard. This stuff up here was Gpios by the FF7F18. I'm going to try hitting the power switch on this, which is soft power. Shouldn't actually turn off. So FF7F18 turns into what now? Still FF7F18. Try the other switch. wouldn't be surprised if these are on a completely different I/O port, like maybe in the same vicinity as the watchdog timer. Oops. Oh, Tuco. Oh yeah, if you have memories of sending files between like a Palm Pilot and a Sony phone or whatever, that was definitely IRDA. Like IRDA was quite ubiquitous for a while, and it would have been the only protocol that would work across manufacturers like that. Yeah, IRDA actually forms some of the, like it uses some of the same protocols that you still see in Bluetooth file transfer. Right, there's an IRDA object exchange protocol that works like Bluetooth object exchange. You could also just use it as a high-speed serial port. I think it was a megabit. And there were a couple of different revisions of IRDA. There was, I want to say there was a version that was like a quarter megabit, and then there was a version that was like a megabit or maybe a little more. Camera's on again. Maybe the camera's trying to tell me this is a good time to wrap up the stream. Yeah, what good is a stream without a cat cam, really? Let's get the most out of this camera while it has temperature. So this is proving to be kind of mysterious. Just for a bit of a recap, I've been trying to get this weird 486 voting machine motherboard to boot. Really, like any kind of normal operating system would be nice, but I've been trying to go for Linux recently. And we had some problems that just turned out to be related to weirdness about the BIOS and the disk addressing. And so partitioning the disk was a bit of a problem. But now that's not an issue, and I can run DOS, I can run Windows 3.1, but I wanted to try something that I'd be likely to actually be able to rotate the screen into portrait mode with, so like X11 probably. There's a nice 2D accelerated driver for X for this graphics chip, which is the Chips and Technologies 65550. So my plan is to just do a pretty normal Linux install on this, but treat it like an embedded platform because I have so little hard disk space to work with. But it's not getting past grub, and it seems like the problem we're hitting is something fairly low level inside grub itself. And I was having what seemed to be a similar problem running ext Linux, so I don't think it's really a grub problem so much as it's something weird about this computer that bootloaders tend to be hitting. So what else could this be? We've ruled out system management mode. It's not an NMI. It's not a regular interrupt. There is one test that I've been imagining we could do that I haven't yet, which is to reproduce the crash and then use the oscilloscope to see what's happening on the bus, like right before Like basically the last things we can see it doing. Like I don't even really know what this crash is. Like is it getting into an infinite loop somewhere? Is it like something in the BIOS hanging? Is it a like more fundamental hardware thing? Like I have no idea. I feel like technologies like IRDA and like there's a mention in chat of like NFC and like QR codes also. Like a lot of these things are kind of explorations in the space of things that could definitely be done with technology, but like we're not sure if people actually want to do them socially. I feel like QR codes had been around for a long time, and then it seems like they have been suddenly getting more popular, but that was due to social changes rather than technical changes mostly. Like people being more willing to point their phone at stuff and less willing to touch things. Oh, is it going to come back if I reboot it? My camera's overheating. Well, I should probably let the camera cool off. Yeah, okay, so it's not going to stay on. I guess this will be the end of the stream. Sorry about that. The abrupt end there. I will let the camera cool off a bit and think about what else we could do to try to fix this problem. But in the meantime, we have Python and weird snippets of assembly language running inside GDB, inside grub on the 486 board, so that's something. Well, thanks so much for hanging out. I'll give Tuco a bunch of pets for y'all. And special thanks to everyone who chips in on the Patreon to keep the streams going. I will see everyone tomorrow. Happy hacking. Tuco's so fuzzy. Extreme KVM switch challenge.